Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Okay, so in section 5.4, Statical Deadlock Prevention. Now in this section, we're going to talk about two conditions, necessary conditions for the deadlock to occur. So let's talk about section 5.4, Statical Deadlock Prevention. Two conditions must hold for a deadlock to occur with reusable resources. One is hold and wait. Now the other one is circular wait. Okay. So hold, wait, and the wait situation is that a process is already holding one resource and requesting for another resource. Okay. So that's a necessary condition. Okay. That's a process. And I have a resource 1 and a resource 2. So process is currently holding one resource. Okay. And then request for another resource. Now that's a necessary condition. So that means even if there's a hold and wait situation, it doesn't necessarily mean there's a deadlock state. But deadlock must be one of this kind of situation, hold and wait. Now the other one is circular wait. Okay, so a process must issue a resource request that close a circular circle involving at least the two processes and the two resources. So that means, the circular situation is like one process P. It is, let's say, currently is holding a resource, okay, and then request for another resource. And then there's another process. That's P1, that's P2. Now this one request for that resource. Okay, but it's currently holding that resources. Now this actually creates some kind of closed circle. Now that's a recipe for deadlock. Okay, so so deadlock is structurally impossible if either of the two conditions are eliminated. So if you break the circle, then deadlock is no longer there. Okay, so hold and wait is a necessary condition. Circular wait is also a necessary condition. Okay. Okay, so we know that two conditions must hold in order for the deadlock to occur. One is the wait, hold and wait. The other one is circular wait. Now, in order to make sure there's no deadlock, we just need to eliminate one of these two conditions. Okay, so let's talk about the first case. How can we eliminate the hold and wait? Okay, there are several approaches to eliminate the hold and wait condition. Okay, one is, so every process must request all resources ever needed at the same time. Okay, so that means if I have a process P1, let's say process P. Now I have three resources, R1, R2, R3. Okay, now P can actually make a request to all of them. Okay, and then if all the resources are available, then you can change all the requests to allocation. Okay, so you can have all the requests and all the allocations. You cannot have both. Okay, so for example, if P is making a request for all three resources and the two resources R1, R2 are available, so you cannot just say, okay, allocate R2, R1, and R2, and still making a request for R3. That's the, hold and wait situation. So this cannot be the case. Now, second one. Now, every process must release all currently held resources prior to make any new request. Okay, so for example, like for approach 2, if process P is currently holding 2 resources, R1, R2, and then now suddenly process requires to R2 and R3 to complete. Okay, if process requires R2 and R3 to complete the job, now you cannot just release R1 and make a request to R3. You cannot do that. Okay, so what you need to do is you have to release both resources, R1 and R2. And then you can make a request to R2 and R3. So you cannot just release one and then still say, oh, I need R2 anyway, so let's just still continue to hold R2 and request for R3. That's the hold and the wait situation. Okay, that's the hold and the wait situation, and we cannot allow this to happen. So we have to actually release both and make actually request at the same time. So even though this approach improves the resource utilization, but still results in repeated request, because originally the process, allocated resource 2 was allocated resource 2, but then when you actually make a new request, you have to release the resource 2 and make a request again. Okay, so that's the second approach. Okay, but anyway, this is going to resolve the deadlock situation by eliminating the hold and the wait. Now the third case, okay, so a process can be given the ability to test whether a needed resource is currently available. Okay, so now let's say that here's a situation. I have a process and 3 resources, R1, R2, and R3, right? Okay, so if the process currently are holding resource 1 and resource 2. Okay, now if the process requests for R3, you cannot directly request for R3 because that's the hold and the wait situation, right? You cannot do that. But this approach allows the process to test the resource 3. Okay, so for example, like the second case, process is holding R1 and R2. Then a process make a request for R2 and R3 to complete the job, and then the process cannot, as I say, cannot eliminate that one and make a request. You cannot do that. But it allows you to test R3. Okay. Now, if R3 is available, then the process is allowed to release the R1. Okay, and continue to hold R2, and then request for R3. And because you already tested for the availability of R3, so R3 is available. So that's the reason why the process is allowed to release R1 and request for R3 and immediately get R3. Okay, so that's an improvement over the second approach. Now, another case is that the process is currently holding R1, R2, and it needs R2 and R3 to complete. And the process tested R3, and find out R3 is not available. Now, what happens in this case? So in that case, this process cannot release just R1. You have to release both R1 and R2, and then you can make a request for R2 and R3. Okay, the purpose is to eliminate hold and wait. So you only have all request or all allocation. Okay, not both. Okay, so that's the three actually approaches that try to eliminate the hold and the wait situation. Now we're going to talk about how to eliminate circular wait. Okay. Now, a circle in a resource graph can be closed only when two or more processes request the same resources but in different order. What does that mean? So that means you have process 1 and you have process 2. Okay, so then you have some resources, right? R1, R2. Now, process 1 may request R1, okay, first, and process 2 request for R2 first. Okay, and then process 1 requires to, request for, so then in this case, process 1 get R1 and process 2, acquires R2. And then process 1 request for R2. So that means process 1 first request for R1 and then request for R2. And then the process 2 request the resources in a different order. Okay, process 2 request for R1. Okay, now that's the potential for the deadlock. Can you see the deadlock? Because you have circle right now, a closed circle. So you have process 1 request for R2. R2 is currently held by process 2, and process 2 request for R1, which is currently held by R1, process 1. So then you have a kind of closed circle, right? Now, in order to eliminate this closed circle, one approach is to assign a sequential ordering, we call it SEQ, to all existing resources. Okay. Now let's take a look at another example. Suppose I have a P1, P2, P3, okay, 3 processes, and I have 4 resources. Let's assume they each has only 1 unit. Okay, so I have R1, R2, R3, R4. And then currently process 1 is holding R3 and process 2 is holding R1 and R2. Okay, and then process 2 requests for R3, but process 2 is blocked because R3 is currently, in the hand of R1, P1, the process 1. Now, if process 1 make a request to R2, now this is going to cause some issue, right? Can you see this problem here? Let's see. You can see the closed circle because process 1 is request for R2, but R2 is now in the hand of P2. Now P2 cannot continue because P2 is requested for R3, right? And R3 is in the hand of P1. You see the circle here? Now P2 requests for this, and then eventually it's a closed circle. That's a deadlock, right? Now one way to, to avoid this is, so let's see. Suppose we, let me just eliminate these things. Okay. Okay. So let's. Okay. So let's actually. Okay. Redraw this diagram. So P3 is no. P1 is holding R3. P2 is holding R1 and R2. Okay. And then P2 is actually holding this. Okay. Now, let's suppose that we actually assign the order. It's called a seq. Okay. Now, seq1, R1, is the smallest one. And the seq R2, smaller than seq R3, and smaller than seq R4. Now, we set up a rule such that a process P already holding a resource Ri. Remember, you have, let's say, R1, R2, R3, Ri, and with the sequence number Ri may only request the resource Rj, where Ri is less than Rj. So that means, suppose the sequence number is in this order. So that means this P, if the P is already holding, the resource is P is already holding the, resource Rj, Ri. So then P can make a request, only can make a request to Rj. Okay, well, sequence number of Ri is less than sequence number of Rj. So that means if we have actually sequence R1, R2, R3, R4, now if process 1 is already holding R3, so then process 1 can only request for R4, which is bigger than R3. Process 1 cannot make a request to R1 and R2 because R1 and R2 are less than, the sequence number of R1 and R2 is less than R3. So let's see. Now in this case, P2 is okay, right? P2 is currently holding R1 and R2. P2 can make a request for R3 because R3 is seq R3 is greater than seq R2 and greater than seq R1. Okay. Now if P3 can make a request to any of these. Okay, because P3 is currently holding nothing, right? So P3 can request for any of these. Okay, so that's the, the general rule to break this, circular weight. Okay, so let's discuss some more cases. Suppose I have process 1, process 2, process 3, and I have 4 resources, right? Okay, let's assume that each resource has only one unit. So R1, R2, R3, R4. Let's discuss various different scenarios. Okay, now if P2 is currently holding R1, okay, and also R2, then P2 can only request for R3 or R4, right? P2 cannot request for any other. Okay. Now, the other scenario is that if P1 is currently holding R3, so P1 can only request for R4. Now, we assume that the sequential number is in this order: smaller than SEQ R3, smaller than SEQ R4. Okay. Now, what about this kind of situation? Is this okay? So I have R1, R2, R3, R4, and R5. Now, currently, P2 is actually holding R1. So that means P2 can make a request for R2, R3, R4, R5. Suppose P2 is making a request for R3, and then P2 actually acquires R3. Okay, that's okay. Now what's next? In this scenario, which resources P2 can actually, request for? Is it possible? Definitely P2 can request for R4, right? And R5, because these R4 is greater than R3, R5 is greater than R3, right? So P2 can request for R4 and R5. What about R2? Is it possible for P2 to request for R2? Now, R2 has actually the sequence number of R2 is greater than the sequence number of R1, right? But it's less than R3, so you cannot do that. Okay. So that's always the general rule. So if we strictly follow that rule, the circular weight is going to be eliminated. Thank you.